Let's wait for a couple more minutes and then we'll start. Am I audible?
Yes, sir.
Okay. It's 3 already. Should we wait or just start? Let's start with the intro, I guess. Others will join. Okay, welcome everyone to the week 2 live interactive session of this course NOC25 EE-39 offered by NPTEL titled Fundamentals of Semiconductor Devices. Uh, this course is taught by Professor Digvijayan, and I'll be the teaching assistant for this live session. Okay, and schedule as usual would be every Sunday 3 p.m. to 5 p.m. These are the details that you can use to reach out to me. And let's quickly go through the guidelines now. In case you have any query, you can just raise your hand or ask it in the chat window. And please ensure that your microphones are muted, especially when you don't intend to speak. I would need your cooperation to make this an interactive session. Uh, so please help me in doing that. I hope others would join because only then this would be an interactive session. Also, please keep the pen and paper handy along with a calculator. Okay. Uh, I hope you would have, uh, I mean, kept the pen and paper handy because I did mention it in the last session as well. So the session recording link and the lecture notes uh, as usual, will be shared by the NPTEL course team. So, prerequisites for this course include the last week's lectures, which covered the following topics. Okay. Uh, we studied about the doping and intrinsic carrier concentration, uh, uh, equilibrium carrier concentration, temperature dependence of the carrier concentration, high doping effects, and incomplete ionization. So these were some topics that were covered or discussed in the last week, and will be doing problems on the same. So this is same. So since there is no one in the meeting apart from one student, is there any doubt in these topics, or should I just start the problems? Okay, no questions. So
Sir, what is free electron, sir?
what
Uh, what is free electron, sir?
uh, could you be a little loud? I'm not able to hear your voice. What is? Could you type it in the chat? Just type it in the chat.
Sir, free electron.
Free electron? I'll write it in the chat. Is that what you're asking?
Yes, sir.
Okay. So an electron or a particle is said to be free when it doesn't experience any potential or when it's not under any potential force. Does that answer it?
Yes, sir.
Okay, thank you. So any other doubt or okay, let's start with the first problem then. So the first problem is first, did you guys solve these problems that I had told you to do so? I had given the C, D, and E as the problems. I mean, as an assignment, right? Because we were running late in the last session. So I told you to attempt 6C, 6D, and 6E. So did anyone try them out? Should I discuss them or have you already tried that out? Because I did not receive an email regarding
Please,
these three.
sir, please
These.
discuss, sir.
Okay, okay. Then I'll discuss. Just a second. Just a second. Okay. Let me change the settings. So let's start with the problem C, 6C first. This is a problem on effective density of states, right? Which is different from density of states. Uh, where effective density of states is roughly the total number of states in energy range of kT near the bottom of the conduction band or the top of the valence band, right? We'll have NC and NV corresponding to those two quantities. And I assume you guys would have gone through the derivation, I mean, how the expression comes about, right? So I'll just write equation. We have the following equation. Okay, this was your A, this was your B. Now let's take my sheet and let see. So this is question 6, part C from week 1 session. So your NC was equal to 2.51. This is your effective mass for electron, right? And this is Rest mass of electron in 0. By 2, you'll have per centimeter cube as a units. So we have following Mn star, as I showed in the last session as well. This is equal to 1.18 m naught. Okay, and your Nc would be equal to 2.51 times 10 to the power 19, 1.18 raised to the power 3 by 2. Uh, so what is the value of Nc that we get? Please use your calculators and evaluate. Does anyone have calculator? Okay, so the value comes about as 3.22 times 10 to the power 19 per centimeter cube. Okay, and if you'll notice this value, okay, so this is it, right? This is the value of Nc. Now, what about uh, your part D? I guess would be on Nv, right? Effective density of valence band states. So the expression that you would use for that is Nv is equal to 2.51 10 to the power 19 Nv star by m naught raised by 3 by 2, right? And then you know that this Nv star is equal to 0.81 m naught, right? And would give you Nv as 2.5 to 10 to the power 19 times this 0.81 raised power 3 by 2. Fine. And this is per centimeter cube. So your NV is equal to 1.83 10 to the power 19 per centimeter. Is that clear? All right. So now the E part is to compute the ratio, right? You need to compute the ratio of effective density of conduction band states, this NC, to atomic density of silicon, right? What is the atomic density of silicon? How many silicon atoms are there in per unit volume in 1 centimeter cube volume? How many silicon atoms are there in 1 centimeter cube volume? You should know this number. Was this taught in the course? How many silicon atoms are there in 1 centimeter cube volume? Please interact. Okay, do one thing, search it on internet and let me know. How many silicon atoms are there in 1 centimeter cube volume? So, in other words, I'm asking for atomic density of silicon. Search it on internet and let me know what is the value. This is the quantity that I'm supposed to compute. NC, I already know is this, right? Your NC is 3.22 into 10 to the power 19 whole divided by, and then this has unit per centimeter cube. Atomic density also has this unit. If I use per centimeter cube unit for atomic density, what is the number? What is the order at least? I'm asking for the atomic density of the silicon. You guys can use internet. I mean, just search it in the Google, atomic density of silicon, and let me know how many silicon atoms are there in per 1 centimeter cube volume. Is the question clear? Please interact via chat or unmute and let me know.
2.33 gram.
No. I need number. How many silicon atoms are there? Right? It is the number. It won't be weight. It would be the number. Number of silicon atoms in 1 centimeter cube volume. Someone is typing in the chat. Yes, that is the correct answer. This is 5 times 10 to the power 22. That is the order. Okay, 5 times 10 to the power 22. Even if you don't remember this 5, at least remember that these many silicon atoms are there in 1 centimeter cube volume. Okay, the order is 10 to the power 22. Okay, now what will be the ratio then? Just divide them. When you divide them, you get okay. I'll wait for the answer. 6.44 into 10 to the power minus 4. Yes, that is the answer. Thanks for the answer. I got the answer in the uh, chat box. Uh, if the student that answered it, Pranav, if your mic is working, please unmute and uh, communicate with me. If not, then you can continue. Uh, we can continue this conversation from chat box. Okay, so this one is done, right? And in terms of percentage, what would be this? This would be 0.06%, right? All right. So now your number of states near the bottom of the conduction band, NC, right? That can be occupied, right? So your NC would be, what is your NC? NC is the number of the states near the bottom of the conduction band, right? That can be occupied, right? Right. And we call this effective density of states in the conduction band. We saw that it is a very small fraction of the density of the silicon atoms. Okay, so it's only 0.06% of, I would say, atoms, the states that are occupied. Okay, this was something that was supposed to be done by you as an assignment. So now we'll start week two. Okay, I'll start week two. I'll update week one slides. If I don't, just let me know in the uh, comments of the uploaded YouTube video and I'll update it. I mean, in case I forget, only then let me know in the comments. So week one needs to be updated because I have added these three. And now week two, right? Okay, now let's try this out. This is the first problem of today's session. Okay, and we need to consider a region of silicon at room temperature. Okay, for each of the following cases, we need to calculate the equilibrium electron and hole concentrations N and P. Uh, we can assume that the dopants are fully ionized. So how will we proceed for this? Is my question clear?
Yes, sir.
Okay. So how would you proceed for the first one? The first one is easy, right? It's pull a sheet first. So this is how you'll write the solution for A, right? You know that for an intrinsic material, your N is equal to P, and that is equal to what are free electron and hole concentrations equal to in an intrinsic material? I'm asking a very basic question, and I expect at least one to respond, if not many. what is your free electron or free hole concentration equal to in an intrinsic semiconductor? Ni, right? This is equal to Ni. Only one student is interacting with me. I would encourage others as well to take part in this interaction because otherwise it would get boring. And what is Ni equal to, Pranav? If your mic is not working, you can write it in the chat. What is this Ni equal to? Because this is also a number that you should know. Right. So Pranav said that it is equal to 1.5 into 10 to the power 10. Okay, I mean, I'll only take the order. You're right, it's 1.5 into 10 to the power 10. I'll take it as 10 to the power 10. Okay, and I'm only considering the order. Okay, and what are the units? Because units are important, right? What is this quantity Ni? Intrinsic carrier concentration. And what are the units for concentration? Per centimeter cube. Yeah, per unit volume, and we write everything in terms of centimeters in semiconductor. So it's 10 to the power 10 per centimeter cube. Okay, so this means that your free electron and free hole concentration is also equal to this 10 to the power 10 per centimeter cube. All right, and else can I show? Okay, now the second part, right? So for the first case, I was not doping, right? It was the material was intrinsic. My ND and Na were zero, right? Now I dope it. Okay, and what is the doping now? I'm doping it with donors, right? And I'm using a donor doping of 10 to the power 13 per centimeter cube. I'm not using any acceptor doping. Okay, so if your ND, if your ND is 10 to the power 13 per centimeter cube, right? And your Na is zero. So how would my N and P change? Any guess?
The number of electrons would increase.
Number of electrons would increase, correct. And uh, how much would they increase by? I mean, let's say we need a number, precise number. So what would be my new N?
Since it is fully ionized, the number of donors is equal to the number of electrons.
Correct. So it's actually equal to your Ni plus Nd. But the thing, your Ni, sorry, your Nd is much, much greater than Ni, right? By what order? I mean, if you take the ratio, this is 1000, right? If you take Nd raised to the power Ni, that is 10 to the power 3, which is a very large number, right? So you can safely ignore Ni, right? And you can write this as Nd, which Pranav answer, right? So this is approximately equal to Nd, which is 10 to the power 13 per centimeter cube. But the question is not yet done, right? We also have been asked to compute the hole concentration. So what about holes now? How would the concentration of holes change, Pranav?
So the whole concentration is Ni square divided by number of electrons.
Correct. And which law are we using for that?
The law of mass actions.
Law of mass action, right? So the law of mass action states that at uh, yeah, at equilibrium, your NP is Ni square, right? So if I know N, I can compute P as Ni square by N. So now that I know that my N is Nd, so I can write P as Ni square by Nd. Can someone quickly compute and tell me what's the answer? Ni square by Nd. You just need to square this term and divide that by this. It is Is the question clear? I mean, it's just a matter of calculation. You don't even need a calculator for that. This is easy, right? What is Ni square by Nd? If your Ni is 10 to the power 10, squaring that would make it 10 to the power 20. So what is 10 to the power 20 divided by Nd? Nd is 10 to the power 13. So how much is this ratio? 10 to the power 7, right? So that is what I'll write. So my whole concentration would be 10 to the power 7 per centimeter cube. Okay, let me wait. Student is typing in the chat. All right, should we then move ahead? Okay, I guess we'll move to the next one. So what about part C now? Focus on this part. Now your ND is 10 to the power 17 and you are doping it very heavily, right? This is your ND, right? Ni plus ND, which is approximately equal to ND, and that is equal to 10 to the power 70. Am I right? Is this clear? Right, just as we did for part B, in similar way, we computed N for this part C, right? Our ND changed, so did our N, right? So now tell me what is P? What would be P? Do it. Ni square would be 10 to the power 20, and you have to divide that by 10 to the power 17. Ten to the power 3, right? Uh, I would encourage you to answer it over mic because that would save our time. I mean, although it's your personal choice, I mean, if you're comfortable using chat, you can do that, but I would highly encourage you to unmute and speak. Doesn't matter if you're wrong. I mean, no one would tell you anything. If you're wrong, I'll correct you. That's it. Okay, now, okay, let's do a quick mental calculation. Okay, now if my ND, this, right, would have been 10 to the power 15. Okay, what are N and P values? Answer it quickly. Now you know the process, right? You should be able to answer it very quickly. If your donor density is 10 to the power 15 per centimeter cube, what would be your free electron and hole concentration, assuming they are fully ionized? N and P, both the values. Answered. If your ND is 10 to the power 15, N and P,
N is 10 power 15, P is 10 power 5.
fine. So the idea is the product has to be uh, equal to 10 to the power 20. Accordingly, you will calculate in your mind. Okay. So I guess this is, this is done now. Now let's try this one, right? Now this is uh, the other way around, right? You have now Na. I want you guys to solve this one. Here, I'm not using donors. I'm only using acceptor, right? And your Na is 10 to the power 70%. So what are my N and P? Answer. Again, they will be,
N is 10 power 3, P is 10 power 17.
P is 20%. Correct. And what is the approach for that? The answer is correct. Just for others, I'm asking. So how should we have proceeded for this one? First, we calculate what?
The whole concentrations.
Correct. We'll calculate P, and that would be equal to Ni plus Na, right? Which is roughly Na. And that's why you answered it as 10 to the power 17 per centimeter cube. And then it was N, which is equal to Ni square by Na, which is equal to 10 to the power 3. So good, you answered it right. Now, the general case, right? You have ND of 10 to the power 17 per centimeter cube, and Na is 3 times 10 to the power 17 per centimeter cube. We write this. What is, okay, ND is, okay, Na is 3 times, right? Now, what would be the values of N and P? See, while solving such problems, you'll approach as follows, right? Firstly, you'll determine what would be the net material doping. Would the net material be P type or N type? Be with me, answer me. I'll help you approach this question. So which one is excess? Is ND more or Na more?
Na is more.
Na is more. So the material is expected to be P type or N type?
P-type.
P-type. So what I'll do is I'll determine the net P-type doping, which would be equal to your Na minus Nd, right? Is this clear?
Yes, sir.
Okay. So which would be equal to 2 times 10 to the power 17 per centimeter cube, right? And once I know this net P-type doping, my N would be simply Ni square by this 2 into 10 to the power 17, which would be equal to 0.5 times 10 to the power 3 per centimeter cube. Is this clear now?
Yes, sir.
Okay. So now we'll proceed to the next question, which is for each of these cases in problem 1, now you need to calculate the Fermi level position with respect to the intrinsic level, right? In other words, I'm asking you to compute EF minus EI, right? And please note that you need to consider sign for this question. So wait. Okay. So for these parts, you need to calculate the Fermi level position with respect to the intrinsic level. So answer for the first part, it's easy, right? What would be the answer for the first part? Please answer it on mic if possible. Anyone? Okay. So for the first problem, where is your EF located? For the first problem, the material is intrinsic. So when the material is intrinsic, where is the Fermi level located? Coincides with the intrinsic level, EI, right? At the middle of the band gap, roughly. So for the first part, EF minus EI difference would be 0, right? Because your EF coincides with EI. So let me write that as for part A, EF minus EI is equals to 0. And the reason that we can write is that EF coincides with EF, right? So that finishes the part A. What about part B now? So the part B motivates us to develop some sort of, I would say, mathematical analysis to approach such questions, right? So do you guys know these equations? I assume you would have seen the n is equal to ni exponential of EF minus EI by KT, or say P is equals to ni exponential EI minus EF by KT. Have you guys seen these equations? Yes, no,
Yes, sir.
right. So from these equations, can we determine EF minus EI quantity? Yes, we can. So please do that and let me know what is EF minus CI. What is EF minus CI?
So it's the temperature, room temperature, sir.
Doesn't matter. Keep it T. Okay, are asking for the problem, right? For the problem, take this as the room temperature. Yes. So your KT by Q would be 0.026, right? But before that, please help me in this. What would be EF minus EI from this? Again, others are not responding. Only Pranav is responding. If other students don't understand,
KT,
yeah, please, KT,
KT into natural logarithm of n divided by ni.
1 of your n divided by ni. Correct. So simple, right? So now we had already computed this, right? If you remember, we computed n for each of these 5 parts, right? We can plug that into this equation and we can determine EF minus CI. Or alternatively, you could have uh, written EI minus EF for this P, right? So either way around, if you had either N or P, you could use either of these two equations to determine this quantity. Where is your Fermi level with respect to intrinsic level? Is the idea clear? What I was trying to say?
Yes, sir.
Fine, thank you. So what would be the answer for part B then? Let's see what was N for part B. Your N for part B was 10 to the power 13, right? And if you plug that here, what is the answer that you'll get? Let's do one thing. We can divide this both sides by Q, right? So that would simplify the calculations because KT by Q is 0.026. Because otherwise, we would have to write it as 0.026 electron volt. So I'm dividing this by Q on both sides. Right? I mean, I divided both sides by Q. Now I'll be talking not in terms of energy difference, but what is the dimension of this potential, right? So now I'll be I'm determining difference that would have units of potential, right? What is the potential difference between EF potential and EI potential? So do this. Turns out that this is equal to 0.18. Okay. So if this is 0.18, what would be EF minus CI? If EF minus CI by Q is 0.18 volts, obviously. So what would be EF minus CI? 0.18 electron volts. Understood?
Yes, sir.
Okay. So similarly, I'll just write the answers and expect you all to verify because only then would you learn. I mean, I showed you how the equation comes about. Now it's only matter of plugging it and then trying to see if the answer makes sense. See, wait, this would say that EF minus CI is equal to 0.18 electron. What I meant by saying that if the answer makes sense, how will you check that? What does this tell you? Is EF above EI or EF is below EI? Is it
EF is
above?
above EA.
EF is above. Now let's see for part B. For part B, uh, our electron concentration was more, right? So we did expect intuitively our EF to be near the conduction band, right? In other words, to be above EI. I mean, are you guys able to understand what I'm trying to point out or suggest? That's how you'll check if your answer is making sense or not. And that's what I meant by this sign. Right? This sign does matter. Because had this for, okay, other thing, for my doping combinations for which the net material would be N type, the sign of EF minus CI would be, if the material is N type, EF would be above or below EI? It would be
Above.
above. So the sign of EF minus CI would be
Positive.
positive. Similarly, if my doping combination is such that the net material is P type, my EF would be below EI. So EF minus EI would be a negative
Neg-
quantity, right? So there would be a negative sign. I hope I was clear. So similarly, you'll attempt the other parts. And if you're not able to, I mean, compute, I can just write the answer so that you could verify. So for part C, your EF minus EI is 0.419 electron volt. For part D, it is minus 4.19 electron volt. Similarly, for part E, the answer is minus 0.437 electron. So this is something that you would verify on your own. Now let's move on to the next question, which is question 3. So now for each of these cases and these cases, uh, you need to now determine EF minus CC. Okay, again, you need to consider sign because sign would matter. So how would you approach this one? The first part is easy, right? What would be EF minus EC for an intrinsic material? I expect you guys to solve it even without knowing equations. So EF is somewhere in the middle of the band gap, right? And EC, you know, what is the difference between EF and EC? Is my question clear?
Half of the band gap, sir.
Half of the band gap. So it would be EG by 2, right? So it would be EG by 2. Now, just a second. See, how would we solve such questions in general? So we know that electron concentration N is equal to NC exponential of EF minus CC by KT, right?
Yes.
So please help me, I mean, in developing an equation for EF minus CC, sorry. What would be EF minus CC?
KT into natural logarithm of N divided by NC.
What? KT by
Like KT into natural logarithm of n divided by NC.
Correct. KT ln of n by NC. Right? And yeah, again, to simplify our calculations, we can divide both sides by Q and then proceed for this. So what about NC now? Did we compute NC already? We did, right? In week 1, this is what we had calculated NC as, right? So we can use this value. This is what you'll use. You'll use NC as 3.22 into 10 to the power 19 per centimeter cube. And you can plug this here. And for all the quantities, you'll use respective n and obtain the answers. Is this clear?
Yes, sir.
Okay. So now let's see the next question. Okay. Assuming silicon with completely ionized dopants, you need to compute N and P for the following case. So now, I mean, I'm not keeping the temperature at room temperature, right? My T is 700 Kelvin. So please tell me what should be the answer corresponding to this. This is a good question. Okay, tell me one thing. What do you expect your intrinsic carrier density to behave as you increase the temperature from you remember at this I mean somewhere in the session I had asked you what is Ni, right? That Ni was at room temperature, right? That 5 into 10 to the power 10 per centimeter cube is a quantity that holds good at room temperature. But when you increase the temperature, your Ni changes. What do you expect? How should your Ni change? Should it increase or decrease with temperature?
Increase its temperature.
Correct. So now that you don't know the exact expression, what I'll do is to simplify this question, I'll give you that quantity, right? Your Ni at 700 Kelvin is equal to 2.865 into 10 to the power 16 per centimeter cube. Okay. Now that you know this quantity, how would you evaluate uh, what uh, NNP? Again, notice in our earlier problems, uh, our doping density was way higher than Ni, right? Earlier, your Nd or say Na for some questions was way higher than your Ni. But now that is not the case, right? This is your Nd and this is your Ni. Very comparable, right? I mean, the if you take the ratio, it's not even 10. So now you cannot ignore, right? So how would you solve it then?
N is Nd minus Na by 2 plus root over Nd minus Na by 2 whole square plus Ni square. So that formula.
Correct. And how does that formula come about?
Charge neutrality condition, if we apply, we can get.
obtain that, right? Correct. So, oh, no, just a second. Are you guys able to see the screen now?
Yes, sir.
Okay, just a second. So this is the equation, right? Your charge neutrality condition states that your P minus N plus ND plus minus NA minus that is equal to zero, right? Now I'll be dropping this term, right? Why? Because I don't have any, right? So I'm left with P minus N plus. Since I have completely ionized dopants, my ND plus is same as ND. Shall write it as ND. So this is equal to zero, right? And uh, P I can write as, help me out. What can I write P as in terms of N? Okay, hint for you. You can use law of mass action for that. What is P in terms of N using law of mass action? What does law of
Ni
mass
square
action?
by N else.
Correct. It is Ni square N minus N plus ND. That is equal to zero. And okay, so what does this imply? This implies that Ni square means N square plus, right? Let's derive the equation for general case first. Okay. And then we'll drop the ND at last. Is this correct? Then I can write this as N square minus ND minus NA. If you're not able to follow, just let me know and I'll repeat. I'm assuming you all are able to follow me, right? This would be the quadratic equation in terms of N. And now what would be N then? Your N would be minus B, right? So it would be ND minus NA. Plus minus, I'll take the positive square root plus square root of B square minus 4AC. So it would be ND minus NA whole square minus 4NI square whole divided by 2. Does everyone agree with this? Would this be the answer that you get? Yes, no,
Yes, sir.
correct. So, yeah, the rain would be ND minus NA whole divided by 2 plus square root of, I mean, I'll incorporate this 2 inside the square root. Let me know if you are able to understand. I can write this as this, right? Okay, sorry, this would be plus, right? This is the formula that you get for N. Now in this, your NA is 0, right? Don't have any. So this formula simplifies very much actually. Right? It's ND divided by 2 plus NA goes. So this is square root of ND square by 4 plus NI square. Is this clear?
Yes.
And when you plug the value of this ND into this equation and use this NI, what is the value that you get? Can you help me out? Okay, I need two values, right? N and P. What would be N? Just verify that it is 6.3 into 10 to the power 16 per centimeter cube. Okay, and P would be, what would be P? Once I know N, how would I compute P?
Ni square
Simple,
by N.
correct. It would be Ni square, N, which if you, I mean, do the calculation, do the math, your P would be 1.3 into 10 to the power 16 per centimeter cube. Notice your N and P, the product of N and P is no longer 10 to the power 20, right? It exceeds that order. Reason being, your Ni has increased because the temperature that we're talking about is much higher, right? It's around 700 Kelvin. So, one last question, since you guys did not ask, so I'll ask it. Why did I solve it for N? I could have solved it for P, right? But why did I proceeded to solve it for N first? Just answer me this and then I'll proceed. Pranav, any idea?
Since the donor concentration is greater than the
Right, right.
acceptor, we consider the N
That's
type.
why, yeah. That's why first we compute electron concentration and then we move on to the whole concentration using the formula Ni square by. Correct. Okay, I guess I should delete this page. What about this question 5? For the case of problem 4, calculate the Fermi level position with respect to the intrinsic level EF minus Ci. Note that you need to consider the sign. Okay. Okay, for this previous problem, now we need to calculate the Fermi level position EF minus Ci. See, you need to use this formula, right? So is the formula that you'll use. Right. Use this formula.
Yes, sir.
So what would be the answer? Yeah, EF minus EI by Q. Just let me know what should be the answer. First, your KT by Q will no longer be 0.026. Why? Because our T is no longer 300 Kelvin. It is 700 Kelvin, right? Because for problem 4, this is the temperature, right? And this is how you do it. Your KT by Q at 700 Kelvin, this is equal to 0.0604 electron volt, right? What is KT by Q at 300? Anyone? Just to brush up your memories. What is KT by Q for room temperature? If for 700 Kelvin it's this, what is the value of KT by Q at 700 Kelvin? Sorry, 300 Kelvin. I mean, that is quantity that you all are familiar, right? 0.026
0 point,
electron
yes,
026. Correct, correct. 0.026 electron. So now that we computed this, what about this? Ni you know, right? What is equal to Ni? This is again at 700 Kelvin. This I gave you here. This is what I'll copy and just paste. Right. This is your Ni. Nu already computed. Now matter of plug and play. So when you do that, EF minus EI by Q is 0.048, right? So EF minus EI is 0.048 electron volt. Is it done? Right. Okay. Now comes the homework section, right? Firstly, let's tell me one thing. Did you guys attempt the homework problems corresponding to week one? Yes, no. If not, do try them out. They were interesting problems. And today I'm giving two more such problems, right? First one is a sample of silicon is doped with, now you have this ND, right? And your donor level ND is 54 millielectron volt below the conduction band bottom EC, right? You ignore the presence of the valence band and assume that all electrons, they come from the donors only. Okay, use the non-degenerate approximation for carrier density, so you can use those exponential expressions. And the effective conduction band density of states for silicon at 300 Kelvin, it's given that it's 2.8 into 10 to the power 90% going to give use this value. And at room temperature, calculate what fraction of dopants are ionized. Okay, try this out. And remember, do not assume all donors will ionize, right? You need to calculate the fraction. What is the fraction of the donors which will ionize? Not all the donors will ionize. Also, compute this thing, the location of the Fermi with respect to the bottom of the conduction band, EF minus EC, which we computed, the quantity which we computed, right? EC minus EF. We did compute that quantity corresponding to some cases. Compute that for this case as well. And how far is it from the donor level, right? Because once you'll determine this, EF minus EC or EC minus CF, you know ED is below the conduction band bottom. So your EC minus ED is this much, right? So once you know EC minus EF, once you determine this, you can find what? Uh, ED minus EF, right? That would be the sequence in which you'll proceed for this and try to compute the exact numbers and not just the algebraic expressions. Is this problem one clear? Is it?
Yes, sir.
Okay. I mean, they are supplementary. Even if you're not able to complete them, it's fine. It's just, I mean, for the curious minds, I would say. So, homework problem two is the band gap of the silicon in electron volt. It varies with absolute temperature according to the following relation, right? Your Eg of T is 1.17 minus 4.70, this expression, right? you need to calculate the concentration of electrons in the conduction band. Okay, calculate N at this temperature, right? Your Ni is given. If it's known that at 300 Kelvin, your N is Ni, and that is equal to this. You have this relation. You can compute Eg at 77 Kelvin and correspondingly obtain Ni at 77 Kelvin, right? First, you'll obtain this Eg at 77 Kelvin. Use that to obtain Ni, and then use that Ni to obtain 8. Okay, I hope this problem 2 is also clear. And for this homework problem 3 and 4, I had planned to include some problems of periods, but I did not get time to add them. Do one thing, try to solve any two unsolved problems from period uh, concerning the topics that you had learned. Okay. Do you know this book, by the way, Robert Parrott, Semiconductor Device Fundamentals?
No, sir.
Not, if not, just search it. And if you get time, read that. Those of you who are interested in higher studies, I mean, this is good book if you are interested in this course. I mean, once you finish this course, if someone is interested in this course and wants to learn more, he can refer to this book and solve problems from this. Okay, that's I mean, we are done for today's session. I hope nobody has any questions. Is that it? Should we end the session then? Please do the, assignments that I have assigned. Okay. I'll anyway share the slides with you, and you'll also get access to this recording. And see you in the next section. Next session. Bye.
Okay, sir. Thank you, sir.
Thank you.
Thank you,